in 3, 2, 1, go.
All right, everybody. Thank you so much for coming out to Astronomy on Tap. We have some amazing talks for you today. We have Anna Hiller and Dr. Courtney Crawford giving talks tonight. But before we get started, just a few reminders. Please be respectful in the chat. We're all here to enjoy some lovely talks. So just keep it clean, keep it respectful. We do have a lovely tip war today. We have the best bird constellation. So please vote. We had an awesome turnout last time. And with that, we can go ahead and get started. So I will go ahead and introduce our first speaker, which is Anna. So Anna Hiller is an ornithologist and PhD candidate from the LSU Museum of Natural Science. In her day-to-day research, Anna aims to understand how new species form through studies on a type of bird called the flower piercer in the Andes of South America. And with that, please take it away, Anna.
Thanks, Ashley. I'm going to go ahead and share my screen here. Okay. Cool. Well, thanks for the invite, everyone. I'm very excited to be here. So today I'm going to be talking about birds in space, which you might not think there would be a lot to say on the subject, but putting this talk together, I discovered that there actually is a lot to say. And it's mostly going to be about especially flight and navigation. You can imagine that that's important both for space and space travel and for birds. But first, y'all are stuck listening to me talk a little bit about what I actually study. As Ashley said, I study a group of birds called the Diglossa flower piercers, and this is them. They're really cool. They come in a bunch of different colors and sizes. They have different colored eyes, different colored feathers, and they have this really cool hooked bill, which you might have noticed. There you go. And it's curved at the tip. And what that bill is for is, unlike a hummingbird that has a curved bill and might go into the flower and pollinate it, Diglossa have a behavior called nectar robbing, where they use that hooked bill to poke a hole in the base or the corolla of a flower and steal the nectar without pollinating the flower. So they're really cool. They're like little robbers. And I'm really interested in them because not only are they really diverse and colorful, but they're also only found in mountain habitats. So they're an 18th species. They're found only in the tropical mountains, mostly in South America. And that lets me study how species form in mountains and lets me understand why tropical mountains are so diverse. The way I do that is called phylogenetics. So you build essentially the tree of life using DNA, and that tells you how different species are related to one another. So in this example, the bluebirds are each other's closest relative, and then the orange birds and purple birds are each other's closest relatives. And my work takes me to some really cool places. I get to go on expeditions to collect samples. So these are just some photos from a recent trip I did to northern Peru to collect samples for my work on Diglossa for my PhD. But that is not what we're here to talk about today. Today, I'm talking about, disclaimer, a subject that I don't study terribly in depth, but I love birds, so I was game. And we're going to talk about birds in space, and specifically two different parts. First, I'll talk about bird biology and ways that it relates to space and the stars. And then I'll talk a little bit about the intersection of humans, space, and birds. And this photo, I'll just say, is a group of ospreys nesting in front of the Kennedy Space Center. And just to give you a taste of what's to come, there are 330 species of birds that can be found at the Kennedy Space Center. So there's more than you might think. The first question I asked making this talk, and you probably asked, is how has a bird ever been to space? And the answer is sort of. This is an example of to my knowledge, the first bird ever flying in microgravity. It's a pigeon. They were taken up in the U.S. Air Force Vomit Comet, is what it was colloquially called. And that's a plane that does these dips to simulate zero G. And then they took pigeons up in it and just wanted to see basically what would happen if a bird tried to fly in microgravity. And this orange arrow you can see is pointing down because the pigeons had a really hard time orienting themselves without gravity to figure out where the ground is. So they were flying up and down and sideways. And there's some really hilarious videos on YouTube if you want to check those out after the talk. But the first, and to my knowledge, only bird that's actually been to space is the Japanese quail. This is a type of quail that is commonly found like in sort of agriculture and like grown for food. So if you ever had quail eggs, this is the egg. This is the species of bird you're eating the eggs of. And they were taken, it was a Russian program. They took fertilized eggs into space a couple different times to see if they could they get a quail to lay eggs in space? Would the eggs hatch? Would the birds be normal? And it took them a couple rounds of bringing the quail into space to finally successfully hatch some birds. And they had to create this incubator. You can see that simulated gravity by rotating. But they eventually were able to hatch some baby chicks in the 90s. And those are the photos on the left here. Those are baby quail floating in zero Gs, which is, again, some really cute videos online. And those are the only birds in space because, as you can imagine, birds cannot just naturally fly in the vacuum of space. They would die. So the only ones in space have been the quail on the International Space Station. But you might ask yourself, how close do birds naturally get to space when they fly, like in daily life? And the winner for that record is Ruppel's griffon vulture, which gets to about 11,000 meters of altitude. And so if the cutoff for space is 100,000 meters, the answer is they don't actually get that close to space, but that's still really high. And a fun fact about this record, how they documented that a bird would get that high, this is in the 1970s, is that a griffon vulture collided with an aircraft at 30,000 feet. And then that aircraft had to land. And so they used the altitude record of that plane to then figure out how high it was and how high the bird was when they crashed. The number 2 and number 3 species holding records are common crane and bar-headed goose. These are long-distance migrants, and they have to cross the Himalayas, which involves a lot of like specialized adaptations to be able to fly such long distances at such great height. So they have things like specialized blood physiology that allows them to deal with the really low oxygen found at those altitudes. And again, how these were studied was just people sort of following birds in planes, which I think sounds like a really cool job. Lastly, I'll say in terms of migratory birds, there's also a lot of cool advances happening right now with GPS technology. So this is a photo in the background of the Icarus antenna on the International Space Station. And this is part of a program to allow monitoring of birds and other organisms with GPS backpack trackers that allow humans to get a better understanding of bird movement and migration, which is really cool. So when birds migrate, you might also ask, how do they do that? Do they ever use the stars to migrate? And the answer is yes. The way this was first documented was in the 1960s on a study of indigo bunting, because many small songbirds migrate mostly at night. And right before they migrate, they have this weird behavior called zugenrue. And it's a type of restless behavior where they'll sort of move around and they'll start to orient themselves in the direction they want to migrate. And you might have heard about the magnetic compass or birds using the sun. They orient themselves in many different ways, but one way they orient themselves is by using stars, and specifically the rotation of stars. So like humans use the North Star to navigate, so do birds. And this study was able to raise birds and use a planetarium to artificially change the rotation of the stars. And they were able to show that when you do that, birds will misorient and go in the direction of the fake, sort of spinning fake North Star rather than the actual North Star. So we know from those studies that birds do use the stars and their rotation to migrate and navigate. One of the latest projects that has come out on birds as they relate to space and their biology was on the 2017 solar eclipse. And this study used weather radar to understand movement and activity levels at different degrees of the solar eclipse being total or not. So as there was like a line of totality where the sun was completely covered. And the question was basically, do birds think it's nighttime and go to sleep, or do they not do anything and they don't care? And what they found in looking at these two graphs, on the left is the solar eclipse, and on the right is the day to nighttime shift. And that birds' activity decreased a little bit, but not nearly to the degree of nighttime. So it seems that sort of weirded birds out. They hunkered down, but they didn't completely go to sleep and stay that way. It was sort of a temporary phenomenon. So that's it for bird biology. I'm now going to switch gears into talking about what birds and space and humans have to do with each other. And I'll start with talking about perhaps the most obvious example, and that is birds inspiring aircraft design. So this is called the field of biomimicry, and it's when humans study organisms to then better engineer sort of technology. And this has been going on, as I said, for many decades with aircraft, but one of the more recent examples is NASA's designing a plane based on albatross wings that are really long and they're curved in sort of a different way than traditional planes. And they also have these streamers, which they're using to study drag and draft, because birds, if you've ever seen birds migrate, they have that V formation. And as a specific, the reason they migrate in that specific pattern is because it decreases drag when bird wingtips overlap when flying in formation. And so scientists to this day continue to study that to increase fuel efficiency in aircraft. Perhaps one of the longest standing overlaps between humans and birds is the fact that birds have inspired humans to name constellations after them for centuries. There's 88 modern constellations, mostly of Greek in origin, that were determined by the International Astronomical Union, which includes several birds, including Cygnus the swan, Pavo the peacock. And this is not just in Greek mythology, but many different cultures around the world have been inspired by birds to name constellations after them over the years. And so these are examples from First Nation indigenous groups in the US, which also have several bird constellations, the loon and the thunderbird being two examples. And then my favorite is the goose. And what's really cool about that is it's the goose is oriented in the direction the stars that make up the goose are oriented in the direction that geese actually migrate. So, fun fact. But perhaps my favorite example of the intersection of birds and humans in space are the birds of NASA, because they're sort of problematic. So this example is from the 1990s, and this is at the Kennedy Space Center, where a pair of northern flickers decided to nest on the Discovery shuttle fuel tank, and they in total poked 71 holes in the insulation. It's sort of like blown foam insulation around the outside of the shuttle. And the problem was that the foam was really easy for the birds to dig into, and so they were really excited about trying to nest in it. But then they would hit the metal behind the foam, and that would stop them from going further and making a bigger hole. So they would give up and move on and make a new hole. So they ended up causing 71 holes, and this eventually led NASA to try and get rid of the birds. And their first thought was well, maybe we can, just sort of get rid of the birds and they'll just go away. But they discovered that birds are protected species. You can't just go and shoot the birds. So they instead had to create the Bird Investigation Review and Deterrent Committee with, yes, the acronym itself spells BIRD, NASA being very, ingenuous. And they had to do things like cut down palm trees where the flickers were nesting and do other sort of deterrence, put up fake models of raptors to scare off the flickers to try and deter the flickers from coming back and continuing to drill holes in the space shuttle. And this continues to be a problem for NASA. You might ask yourself, what happens when a bird hits a space shuttle during launch? Has a bird ever hit a space shuttle during launch? And surprisingly, the answer is yes. On the left here, this is a photo of a turkey vulture hitting the Space Shuttle Discovery external fuel tank during liftoff. So the turkey vultures were really, really abundant at the Kennedy Space Center for a long time, and they had to institute the roadkill roundup program as part of this bird abatement. And basically, they go out every day and survey the whole Space Center for roadkill, and they remove it to try and decrease the population of vultures because vultures are scavengers, among many other sort of steps that NASA is taking to decrease the population of birds. And you might not think that like birds hitting space shuttles is like a super big problem for anyone but NASA. But actually, in the United States alone, over 7,000 bird aircraft collisions were reported in 2007 alone, and over 80,000 between 1990 and 2007. But we're still like trying to learn about why birds hit aircraft, which species of birds pose problems for aircraft. You can imagine something like a hummingbird probably wouldn't do much to an aircraft, but something larger would, and perhaps most famously on the left here, the U.S. Airways flight, which landed in the Hudson, you might remember in 2009, crashed after colliding with a flock of Canada geese. So it's not just what species, but how many. And on the right here is an example of what happens when you hit probably a large bird. I don't think they ever figured out what species this one was, but this is the nose of a Delta Airbus caved in post bird strike. So how do we figure out what species are crashing with aircraft? And how do we then, because if we know what species it is, we can then help with the abatement process and make the habitat around the airports less suitable for the birds, and then they'll go away, hopefully. Well, the way we do that is by comparing the remains of birds that crash with aircraft to reference collections. So this is a photo of the Smithsonian bird collection, and every bird has a data tag with the species and the location it's found. And then you can essentially compare the remains of the birds that crash with aircraft to these specimens and try and figure out what species they are. So here's an example. This is Carla Dove on the left. She's the lead of the feather lab at the Smithsonian that does this sort of wildlife forensics. And you can see that if you pull out the specific feathers that you get from the aircraft, this figure on the bottom is from that Hudson River crash where they pulled feathers and they were able to compare them to specimens to figure out that it was in fact Canada geese that caused the problem. And this is where I come in, because while I don't study birds or space or aircraft or anything, I do work in a natural history collection. And it's just one example of the many ways that natural history collections can allow us to answer cool and weird questions we maybe never would have thought of. So support your natural history museums. And LSU has one of the best natural history museums in the United States. So if you haven't seen it yet, come check us out. We're on campus in Foster Hall. So with that, I'll say thanks to everyone who gave me ideas for this talk. Thanks to Tabby's Pottery Group for the invite. And I will take any questions.
Awesome. Thank you so much, Anna. That was really interesting. I love learning about how, birds they're just there. And I think it's hilarious that NASA has to go and clean up roadkill. I just can't imagine working for NASA and going out and they're like, oh, I'm on roadkill duty. So, all right. So we do have a few questions, and just a reminder for everybody, if you guys have questions at any point, go ahead and type them in the chat. I will be the moderator and ask them to Anna. And yeah, so our first question are, so far in the future, there won't be a North Star. So would something like that affect bird navigation?
Probably when the North Star like blinks out, then yes, but it's more about the rotation of all the stars. So they fixate on sort of the pattern rather than like one specific star is what they think. So in that planetarium example, they just like changed the rotation, and that's what caused them to go in the wrong direction. So if all the stars disappeared, then they would have problems.
Awesome. Well, thank you. Okay, we have a question from our other speaker of the night. Why can't birds fly in space? So like in zero gravity, essentially.
So they can fly in zero gravity. They just can't orient. So they'll fly poorly. They fly down, they fly sideways, they turn around, they fly. If you put a hood over a bird, they'll fly backwards in zero gravity, like reverse somersaults. They can't fly in actual space because there's no air. So like the lift that gives bird wings the ability to support them is from air molecules, and there is no air in space. Not to mention all the other problems with like, why can't humans just exist in space? You need a spacesuit. But specifically with flight, yeah, you need the air to provide lift.
Okay, awesome. Yeah, it's like probably would just be as interesting as cats in space that Tabby gave the talk on. Okay, so there is one more question. Let me go ahead and pull that up. Has anyone ever tried to, I know you mentioned that they've brought quails and everything like that up into kind of on the a little bit higher up. But has anyone ever tried to teach a bird to orient itself in microgravity?
Yeah, so that's where the simulations are from. I'll say that now there's like a lot of permits to work on live birds. So it's really difficult to get permission to do like training. Like if you're working with adult live birds, it's a lot more complicated. In terms of like bringing live birds up to the space station, there's a lot of other complicated things going on. Like birds have difficulty swallowing in space because a lot of bird species use gravity to help them digest food. So they have a hard time eating. That's just one example of the challenges of working with like a complex vertebrate species versus, you know, like a microbe in space. But yeah, so to my knowledge, no one's tried to train birds to fly in space.
Yeah, that actually answered my next question of if they had plans on trying to bring birds up into space to see, or up to the ISS a little bit more to see if they could kind of monitor how they react or they act. But you just answered that.
Yeah, they bring. I think there's continuing interest to bring like eggs and sort of bird embryos to study development. But I think like full adult birds would be problematic, and birds need a lot of space. Mm-hmm. And the space station's pretty small. So I think that's part of it as well.
Yes. Okay. So our next question is, so you mentioned, you have these launches going on. I guess, why do the birds just like kind of stay there? Like if you have this rocket launching, it's this big loud explosion essentially happening, and they just kind of stay there, or they fly kind of directly at it. Do you know why they don't kind of veer off course or fly away when that happens?
Yeah, I think it has to do with the speed. So this is also a problem with roadkill, right? Like why do things hit cars? It's because in nature, almost nothing goes that fast naturally. And so birds they don't know like to get out of the way because they haven't evolved that reaction. They haven't like evolved to exist with space shuttles. So they just don't know what to do. A lot of like stuff, a lot of species of birds, but also mammals will like freeze in place. Or they just, like a turkey vulture doesn't fly super fast. So it depends on how fast the space shuttle is launching. I think quite quickly. So they probably also just can't fully get out of the way of not just the space shuttle itself, but all the turbulence that causes is going to cause the birds to like go spinning and not really be able to fly super well.
Yeah, that makes sense. Our next question is, do you know if NASA has ever adopted like the best practices from so the Air Force has the BASH program, which is the Bird Airstrike program. Do you know if they've kind of looked into that or used anything from that program at all, if you know anything about it?
My suspicion is yes. NASA is like, I think it's considered a military base, or it's at least heavily involved with military, and they like coordinate with the Air Force for their launches and everything. So I'm assuming yes. I think a lot of like the woodpeckers, a lot of those are like older examples, and so I think nowadays there's a lot more concern about like reducing aircraft collisions and going about that. So my suspicion is yes, but I don't know if there's like specific things that NASA can't do because it's spacecraft instead of like fighter jets. I don't know how that might affect what NASA does, but my suspicion is yes.
Okay. We do have another question. So someone in the audience said that they heard a lot of talk in the last year or two about people who want chickens in the ISS. And so that they were thinking about bringing eggs because, bringing eggs to Mars, that way they're not stuck with, freeze dried meats or no meat at all. Do you think that will ever happen?
Ooh. Well, that was the original idea with those baby quail was, can we use quail as a food source? Because quail are a little bit smaller than chickens. I don't know. I don't think so. I think that chickens and quail are like maybe for sort of small space travel to the ISS or something, but I think all the way to Mars, I just can't imagine the birds living that long in space. The experiments they've done, they were only in space maybe like 14 days in total, like on the order of days in total. So no one's ever like brought a pet chicken up to space for like a year and had it live.
Yeah.
I was mentioning the issues of feeding, like that's just one challenge they've had. They had to, in order to get around that, they had to outfit the quail with these little like harnesses to strap them down so their feet were touching the floor, and then they would like start to eat. But in terms of taking chickens to Mars, you also have to get the birds to like reproduce to make it sustainable. And that's really hard too, because birds, they need to be like at least moderately like happy and like in a good environment to reproduce. So they've attempted to bring up birds and have them basically from mating, from inception all the way to becoming an adult bird. They attempted that and it didn't work because the birds just like wouldn't even mate, which is step one. Mm-hmm. The only live birds that have been in space, those quails, were already fertilized eggs brought into space. So yeah, you have to like set up chicken Tinder or whatever on the space station and get it to work, and then Tinder. You can maybe bring the chickens to Mars.
That's fantastic. Okay, so we have time for 2 more questions. Our first one being that if you were to design a plane or spaceship after a bird, which one do you think it should be?
Ooh. Oh, I want a hummingbird plane. That'd be super cool. They have, they're the only species of birds that can fly backwards. And they have really cool wings that have evolved to sort of, instead of just flap, they rotate. And you could have sort of like a plane helicopter hybrid based on hummingbird. That'd be pretty cool.
Yeah, that would be really cool. Okay, so this, of course, is our classic question. We ask every single AOT speaker this, except this night, it's a little bit of a twist, and you're welcome to answer just the general question, but we want to know what your favorite bird Pokemon is.
Oh, man, my favorite bird Pokemon. I grew up watching Pokemon in the 90s, and there were like way fewer, so I'm going to go with Pidgeotto because that's like the OG bird Pokemon. Yeah.
And a quick follow-up that way, if you did have a different favorite Pokemon, what is your favorite Pokemon?
I was going to say Bulbasaur because I've gotten really into native plants over pandemic. So I really like that Bulbasaur has like the flower and sort of grows.
Fantastic. Well, thank you so much. We are ready to switch to our next speaker. So thank you so much for coming out and giving this amazing talk on birds in space. I know I learned quite a lot about it, and also through your questions. So thank you so much, Anna.
Cool. Thanks. This was fun.
Alrighty. So next up, we have Dr. Courtney Crawford. She recently defended her astronomy PhD at LSU. She studies a special type of hydrogen deficient stars called our corona borealis stars. And fun facts about her is that she likes video games and her recent obsession is Persona 5. So please give it up for Dr. Courtney Crawford.
Hello. Yes, it's me again. You thought you could get rid of me, AOT fans. You cannot. I'm here to stay. No, it's okay. So yeah, you can see my screen, right?
Yes.
I think great. Okay. Yes. So today I am going to talk to you about auroras on Earth and elsewhere. I do not study auroras, but I think they're really cool. And so yeah, everyone should think they're really cool because they are. Anyways, just a quick note, I'm going to use auroras and aurorae interchangeably because they are both correct plurals. So just keep that in mind. Just to start, I want to dedicate this talk to Dr. Arlo Landel. Arlo was an emeritus professor at LSU for many years, and he was very beloved in our department, and he passed away earlier this year. I originally wrote this talk to impress him because he was in one of the first groups to overwinter in Antarctica, where he actually studied the southern aurora. So I want to dedicate this talk to him. So yeah, we'll start with auroras on Earth. So probably your first question whenever you think about auroras is what are they? How do they work? Why do they exist? Where does the light come from? So I'm going to take you on a story of basically a particle coming from the sun and then eventually turning into an aurora on Earth. So the sun itself has a constant wind and sometimes has these things called coronal mass ejections. So basically the sun always has these charged particles coming off of it. That's the solar wind. It has a constant wind. And then sometimes it'll have little bubbles that come off. Here you can see a GIF of one of them where it's got these bubbles of material that will come off of the sun. Those are called coronal mass ejections. So the sun is always kind of emitting these charged particles. And those particles move away from the sun, radially from it. And as those particles get closer to the Earth, they start to encounter the Earth's magnetic field. So here I have just a picture of the Earth's magnetic field in blue, and this orange here is actually the magnetic field of the sun. So you can see the particles come from the sun, which would be over here, move towards the Earth, and they get caught in Earth's magnetic field. So these lines here, if you've never seen a magnetic field plot before, these are called magnetic field lines. And you can think of them as arrows, where this is sort of the path that a typical charged particle is going to try to take in a magnetic field. So usually it's going to point either towards or away from one of the poles. And so any particle sort of here will try to go towards the poles in a magnetic field. So those particles are coming from the sun and they get trapped in the Earth's magnetic field. But they do have some angular momentum. They have some orbit associated with them. They're not just going to follow straight through the magnetic field lines. They actually rotate, orbit around the magnetic field lines and spiral in towards the north and south magnetic poles. So when those get towards the magnetic poles, they start spinning really, really fast. They start moving really fast because the magnetic field is very strong at the north and south magnetic poles. And what happens is when those particles are moving really fast, they actually bump into particles in the Earth's atmosphere. So here's just a picture of an infographic of what the Earth's atmosphere looks like. And up at the top of the atmosphere, we have something called the ionosphere, where there's a lot of charged particles up in the upper atmosphere of Earth. So what happens is these solar wind particles that are moving really fast bump into other particles in the Earth's atmosphere. And that imparts some energy into those atoms, those ions up in the atmosphere. So those atoms in the ionosphere are very energized. And whenever an element is energized, over some time, it will relax back down to a lower energy state. So here's just a picture of an atom where you have some electron that jumps down to a lower energy state. And when that happens, you emit light from that element. So basically, these atoms that are up in our atmosphere are very energized, and when they relax back down, they emit light. And that light is associated with the element. And that's the actual aurora that we see. The light that comes from these atmospheric molecules, atmospheric particles relaxing back down, that's the aurora that we see with our eyes. So just to pull it all together, say it all again, the sun is emitting a wind and sometimes coronal mass ejections, which are sort of like solar flares. That material moves away from the sun and towards the planets, in this case, Earth. And those particles get trapped in our magnetic field, which is here in purple. And they'll spiral in towards the north and south magnetic poles of the Earth. Once they get towards really close to the north and south magnetic poles, they're going to be moving really fast. And they're going to charge up the atoms in our upper atmosphere. And when those atoms in our upper atmosphere relax back to lower energies, they're going to emit light. And that is the aurora that we see. So there are two aurora on Earth. One is the aurora borealis, which is the northern lights as we usually know it. But there's also the aurora australis, which is the southern lights. And in fact, you may be thinking, do they occur at the same time? Yes, they do. They occur at the same time, and they tend to have very similar patterns. They tend to have very similar patterns and occur at the same time, in the same way, with the same colors. So that's really interesting, and that's actually what Arlo was studying back when he spent his time in Antarctica. So this auroral oval here that you'll see labeled is actually the ring around our north and south magnetic poles where the aurora happens. And with high solar activity, that auroral oval will move towards the equator. It will move further down the Earth. And at periods of low solar activity, it will get a little bit smaller and be sort of localized to the north and south poles. So you can imagine that if we had a crazy solar storm, we would be able to see aurora very low on the Earth. In fact, there's one such event that was recorded. It's very famous. This is called the Carrington event, and it occurred in 1859. So what happened was on September 1st of 1859, Carrington observed a very bright solar flare on the sun. It was actually the first solar flare ever recorded. And at the time, we did not know much about solar flares and the connection with the aurora. However, the next day, September 2nd of 1859, there are recordings of aurora being visible at 20 degrees latitude. Now, for reference, a typical aurora is between 60 to 70 degrees latitude. So here on this plot of the Earth, that would be up here in the Arctic Circle. But we're recording auroras at 20 degrees latitude. That's lower than the Tropic of Cancer. For reference, Baton Rouge is about 30 degrees north. So we would be able to see aurora in Baton Rouge and even further south. Now that's really cool, and it would be really pretty, but it's also kind of scary because what actually happened was this caused a lot of fires at telegraph stations. So this was when the telegraph was first sort of being built-ish. And basically, the magnetic field in the Earth moves around when there are solar storms like this, and it sort of messes with Earth's magnetic field. And that magnetic field changing induces a current in the telegraph lines, which then caused a lot of fires throughout the world. And in fact, if the Carrington event were to happen today, it would knock out our entire electrical grid, and we would be in a lot of trouble if something like this were to happen today. And we have not really any way of protecting against it. Now, solar storms like this are very rare, but there are solar storms commonly. And in fact, here is one such solar event that happened just earlier this year. I'm going to mute this when I start it. Okay. So you can watch this here while I'm talking, but at the end of January, beginning of February, there was a small coronal mass ejection that was observed on the Earth. And what happened was they estimated that the material from the sun was going to reach Earth on February 2nd to 3rd. And on February 3rd, there were 49 Starlink satellites that were launched from Earth. And basically, there was a lot of increased drag from the magnetic storm's effect on the Earth. So whenever the solar wind hits us, it messes with our magnetic field and it changes the density of the atmosphere a little bit. So there was a lot more drag than they were originally accounted for, and it knocked out 40 of the 49 satellites. So here you can see what it looked like over Puerto Rico, where they looked like meteors, right? And these are, in fact, the 40 Starlink satellites just going down over Puerto Rico. Now, this wasn't necessarily dangerous. I don't believe there was that much property damage, unless you're SpaceX. But it is just evidence that solar storms do still affect us, and we are still looking out for them, even if we're not looking out for a Carrington-like event. And if you're wondering, yes, there was also an aurora that day. So here's a picture of the aurora from February 3rd, where you can see something here. I like to think it's a Starlink satellite, but I might be wrong. I don't know. Anyways, there was an aurora that day as well, and it was quite strong. So that solar storm did also make an aurora. Now, another thing that we can think about when we're looking at aurora, and maybe the first thing you think about when you think about an aurora, is how colorful they are. And the colors actually mean something and can tell us information about where the aurora is occurring. So the colors that these aurora have are caused by the excitation of different elements within our ionosphere. So the most common color for an aurora is the green color. This is associated with an oxygen transition and a couple of nitrogen transitions. So this is the most common color you're going to see if you ever see an aurora, not only because this is a high density region of the atmosphere. So this is the sort of intermediate altitude area of that, but also our eyes are very sensitive to green. So we just tend to see green a little bit better, but also it's a high density region and it's a very common transition. The second most common color that you're going to see in an aurora is the red color. That's going to be a slightly higher altitude than the green line region, and it's going to be a little bit more rare. This is associated with an oxygen transition, a different oxygen transition. So just for reference, the color you get from your element relaxing back down to ground state is really indicative of what conditions that atom was in originally and what conditions it's going to be in later. So things like density, temperature, all that kind of stuff. The least common color that you're going to see is blue, but if it's a very high solar activity day, you might see some blue. That occurs at the lowest altitudes within the atmosphere, and it's predominantly from ionized nitrogen, but it's really rare. So if you ever are looking at a photo of an aurora and you see that it looks really blue or really, say, purple, just know that the colors on that aurora photo have been edited. And if you're ever looking at one and you see a lot of green, that one's probably as close to your real, what your actual eyes are going to interpret. But aurora also emit in the UV, infrared, radio, and X-ray as well. It's just that obviously we can't see those with our eyes, but we can observe them in other ways. And in fact, when I talk about aurora on other areas, you're going to see this come back. We're not going to be able to see them we're going to see different wavelengths of these aurorae. So here's just a video from the ISS flying over the southern pole where you can see some of the aurora. You can see it looks like a big oval, and you can see the red line region is sitting on top of the green line region. So that's really interesting. And here's just a screenshot of a different one where you can see still the green line region is clearly the brightest and the part that you see the most, but there's also this thin, sparse red line region sitting above it on the atmosphere, sort of glowing outside of the Earth a little bit. So it's really interesting. What can we learn from aurorae? Obviously, we can figure out what element is producing those colors, but we can also get some other information. And I included a pretty nice quote from a researcher where I got a lot of this information, where he said, auroral forms are like fingerprints linking optical features to physical phenomena in the near-Earth space. So aurora and auroral forms are a lot like fingerprints of our magnetic field, our atmosphere, and the effect that the sun's activity has on our magnetic field and atmosphere. So here we can see just a few different kinds of well-known auroral forms. These are some of the most well-known auroral forms. Here you can see the glow type auroral form, and similar to that, little patchy areas, the patches. There are also arcs, which are long, just curved regions of space. And then there are these little bit more curly looking ray areas. So these are the most common auroral forms, and they're really well known. In fact, you can find historical papers of these where people have drawn them by hand, which is kind of neat. But recently, there have been a couple new auroral forms that have actually been discovered. So here's one. This is Steve. So in 2017, Steve was discovered by citizen scientists. And when you discover something, you get to name it in astronomy. So the citizen scientists named this particular aurora after a scene from Over the Hedge. This scene.
What is this thing?
Heather, no!
I'm scared. Me too, Mommy.
Shh, it's okay. It's just what is this thing?
It's Vern. Well, it's obviously some kind of bush.
I would be a lot less afraid of it if I just knew what it was called. Let's call it Steve.
Steve?
It's pretty name.
Steve sounds nice.
Yeah, I'm a lot less scared of Steve.
Oh, great and powerful Steve! What do you want?
Yeah, so in classic astronomer fashion, even though they're citizen scientists and not trained astronomers, they named it just like an astronomer would. So Steve stands for Strong Thermal Emission Velocity Enhancement, if you believe that. But actually, Steve is not an aurora. What researchers did was they sent an actual probe into the aurora, and they actually found that it wasn't not an aurora at all. It's actually a ribbon of hot plasma up in our atmosphere, very high up in the atmosphere, 450 kilometers, and it's really hot. It's 3,270 Kelvin, which is about 3,000 degrees Celsius. So really hot, and it's moving really fast at 6 kilometers per second. So it's not an aurora, but it looks like one, and maybe you could have guessed that it wasn't an aurora because it's not green. But in fact, there is an aurora associated with Steve called the picket fence aurora. And this one is a real aurora. You can tell because it's green. So this aurora is caused by electron precipitation from the ribbon of plasma. Basically, Steve heats up the atmosphere around it, and then that atmosphere relaxes back down to ground state and produces an aurora. This is an interesting aurora because it's occurring outside of the auroral oval. So it's not caused by solar activity, which is really interesting. So auroras don't necessarily have to be from solar winds. One other one that was discovered by citizen scientists recently in 2020 is an aurora form called the dunes. So here's a video of that where you can see what it looks like, where there's the normal auroral arc, and then the dunes are over here. You can see they look, stop it. You can see they look like sand dunes, which is, I believe, how they were named, where it looks like these really wispy, airy regions that have some oscillation up in the atmosphere. Now, I would tell you what these are from, but there is not a paper on it yet, as far as I know, because this is a really recent discovery. But I believe the current leading theory is that it has to do with abundance, like element waves in our upper atmosphere. So basically there's oscillation of how much oxygen is up in our atmosphere at that elevation or that altitude of the atmosphere. But at the end of the day, they don't actually know. So that's a lot of stuff about aurora on Earth. Let's talk about aurora elsewhere, because we can see aurora on other planets. And in fact, we've seen aurora on 4 planets within the solar system. And I'm going to talk about 2 of them. You can probably guess which 2. The first one is Jupiter, our big friend. Jupiter's magnetic field is about 15 times stronger than Earth's magnetic field. And it's a really complicated magnetic field. It actually attaches to the 4 Galilean moons. The magnetic fields are connected. And also the aurora is actually connected to this magnetic field as well. So the aurora is also associated with the position of the 4 Galilean moons. So here you can see a picture where you can see this one is connected to Io, Ganymede, Europa. And how they believe this works is that not only is this affected by the solar wind, but it's also affected by volcanic plasma coming from the planets, from the moons, the 4 Galilean moons. And that would be why Io's is so particularly strong, since Io is the most active planet or moon. I'm so sorry. Most active moon in the Jupiter system. But here you can see it has a normal auroral oval. It has these little weaker ovals within the main oval. You can see it occurs on the north and south poles of Jupiter. And here's just a picture of what it would look like on the planet itself. I want to note that these are UV images of the aurora. So these are not visible images. The aurora on Jupiter is not blue. We are observing it in the UV, which I said our aurora emits in the UV as well. It's just that we can't see, since the atmosphere is so dense on Jupiter, we wouldn't be able to see the aurora in the visible. So Jupiter also has an aurora. We've also observed aurora on Saturn as well. Now, Saturn's magnetic field is actually weaker than the Earth's magnetic field, which is kind of interesting. And Saturn's magnetic field has no obvious connection to its moons or its ring system, which is a type of moon. So it's kind of a very simple aurora compared to Jupiter. And here you can see it's on the north and south poles. Here's what it would look like on Saturn. Note, again, it is not blue. But you can also see that it moves around as, time passes, just like how the Earth's aurora moves around and Jupiter's aurora moves around. So we've also observed aurora on Mars and Venus. I'm not going to talk about them at length because they're a lot weaker detections and they're in different wavelength bands. But I want to talk about one other system, which is actually an extrasolar system. This is a brown dwarf star that was found approximately 18.6 light years away. And in July 2015, they believe they viewed an aurora with the VLA. So that's the Very Large Array, which is a radio telescope. So they believe they were able to detect hydrogen emission on the pole of this brown dwarf, and that it was about 1 million times brighter than Earth's aurora. But it was a hydrogen emission, not any sort of oxygen or nitrogen emission. Now, what is it from? We don't know. This is also a very weak detection. Astronomers are wrong a lot sometimes, but this is still an exciting prospect to think about. Can we see aurorae on brown dwarfs outside of our own solar system? And what does that mean for how they're formed? If this star has no companion, then what is causing the actual aurora that's on this brown dwarf? So regardless of whether or not this is actually an aurora and whether or not we've actually observed it, it's still an interesting prospect to think about. There's no particular reason that other extrasolar systems couldn't have their own auroral systems. So to summarize everything that I've said, basically aurora on Earth are caused predominantly by the sun. The solar winds travel down Earth's magnetic field lines, excite our atmospheric molecules, and when those atmospheric molecules relax, they emit light, particularly green light, usually. And one thing I hope you also take away from this is that viewing aurora and studying them is a phenomenal way to participate in citizen science. And auroral scientists are really accustomed to listening to citizen scientists and allowing them to be in papers and things like that. And also aurora are visible on other planets too, perhaps even extrasolar systems. So that would be really cool. They're just really neat things to think about. And if you want to view one, which you probably do, and you want to know my advice for if you want to see it, my advice is to head north. Usually the aurora is between 65 to 70 degrees latitude. So that's quite north. You can kind of pick wherever you want in there, but you probably want to go for somewhere where it's relatively dry. There's not a lot of precipitation. But if you want day-to-day updates, or if you want to be really sure you're going to see one, what you should do is go to spaceweather.com for updates on solar flares, coronal mass ejections, and potential auroral activity. Spaceweather.com has a lot of information on when the last solar flare was, when it will hit the Earth, how strong it was, how many sunspots are currently on the sun. It could also tell you what latitude aurora are going to be most likely to be seen on a particular day. So if you're ever like really wanting to go see this, I definitely suggest going to a website like this and looking up what day-to-day stuff is going on and give yourself the best shot at seeing it. So with that, I hope you enjoyed this. Thank you for listening. I know I'm not actually an aurora astronomer, but I think they're really neat. So hopefully you do too. I'll take any questions y'all have.
Thank you, Courtney. That was very, very interesting. We do have a few questions for you. So our first one is going to be, if I can pull it up, could you have aurora without a thick atmosphere?
Yes, I presume, right? Because Mars doesn't have that strong of an atmosphere. So yes, the issue probably would have to do more with the magnetic field. So usually magnetic fields and atmospheres kind of go hand in hand. I am not a planetary astronomer, so just stop me if I say anything wrong. But yeah, typically those go hand in hand. And so yes, but it's going to be really weak on a planet with a weak atmosphere and a weak magnetic field. But you can still see them. We see them on Mars. So presumably, yes.
Awesome. Okay. So does climate change have any effect on the aurora? Would you happen to know that?
I don't think so. I would presume not, really. It might have effect on, say, what element, maybe what color. If I had to guess, carbon dioxide molecules aren't really present at that part of the atmosphere. So we probably wouldn't be seeing effects from like greenhouse gases because those are molecular things. And we're looking predominantly at ionized features and atomic features up in that part of the atmosphere. So I would say probably not that much, but it's an interesting idea. I don't think you would get that much effect on the magnetic field in the atmosphere from climate change itself.
Cool. Sorry, just reading our chat. We have some lovely comments from Jude.
Hi, Jude.
Would it be possible to have an aurora with basically all of your colors of the rainbow?
So within an aurora, I mentioned green, red, and blue. Obviously, if you're looking, say, from underneath, those colors are going to all blend together and they're going to appear to be different colors to you. But then if you wanted to have all of the colors of the rainbow, that would be a bit more complicated because a lot of our perception of color has to do with the difference between additive and subtractive color. And as far as I know, it would be really hard to get a lot of the colors that we're like really familiar with just by adding light together, since a lot of them are like due to pigments and that kind of stuff.
Interesting. That's really cool. Does each Galilean moon have its own bow shock where the magnetic field changes direction in front of the planet and moon, or are they all inside of one bubble?
I do not know. Maybe. Definitely like a really fascinating question. I, alas, do not know the answer. However, yeah, I would think they might have little ones, but they would probably also be encompassed in a bubble. But I don't take my word for it.
Okay. Yeah, just that probably is pretty complicated. And I know astronomers like to kind of sort of pretend magnetic fields don't really exist, but they do. But they also don't.
I'm sure some planetary astronomer is crying in a closet right now about that question.
I can imagine. I know Dr. Hines would probably just be like, absolutely not. I'm not answering this question. Okay. Are there any more questions from the audience? Anything before we move on to our classic traditional question that I'm sure Courtney has been preparing for ever since she found out she was giving this talk?
I was just surprised to see while I was talking, the chat was just going. I was like, dang, what are you talking about?
All right. So I don't see any more questions. So I will go ahead and move on with our classics. So I'm actually going to hit you with 2 questions to keep with the theme of Anna's talk. What's your favorite bird Pokemon?
I have my friend Swablu. He's a little cloud bird. I don't know if he's actually flying type. However, he looks like a bird. So I think he counts.
I think he counts. And then, of course, what is your actual favorite Pokemon?
Okay, so I have many. There's a lot of things going on here. I have many favorites. These are some of my favorite Pokemon. I am a little bit insane. I like cool guys, and I do indeed have a Squirtle tattoo. Fun fact. But actually, after playing Legends of Arceus, I think Cleaver is one of my new favorites. But close second's got to be this little dude. Look at his face.
It's very cute. Very cute.
So yeah, Cleaver is actually my favorite, but they don't make plushes for him yet.
Well, hopefully they make plushes soon, so you can get that to your collection.
Yeah, before I go to Australia.
You're getting comments on how you came prepared with props. So
okay, that's from Ethan. You did the same thing. Don't come to me. Ethan had his own props too.
All right. Well, I don't see any more questions. So thank you so much for giving your talk today. It was very interesting. And I also wish you the best of luck in your future, Dr. Crawford. Thank you so much for coming out, and thank you to all that attended. If you haven't already, check out our tip war. Hopefully participate, vote for our winning bird constellation. And with that, thank you all so much for coming, and we will see you next month.